Hello everyone, in this video we will cover the section 2.7. In this section we will learn a numerical approximation for the solution of first order differential equations, which is called Euler's method. Recall two important facts about the first order initial value problem, dy over dt, which is here we have the most general form such equations. If the function f and its partial derivative with respect to y are continuous, then the initial value problem written here has a unique solution in some interval surrounding the initial point t0. If you remember, without directly solving the differential equation, we can understand whether it has a solution or not by checking that the functions written here are continuous or not. Second, it is usually not possible to find the solution by symbolic manipulations of the differential equation. Namely, when we consider any arbitrary differential equation, it is not easy to find its solution, and sometimes it is not possible. Okay. Up to now, therefore we should consider an easy method for every differential equation, because in the previous sections we are interested in special differential equations like linear, separable, or exact, or that can be transformed into one of these types. But by finding a method which is a numerical method for the solution of differential equation, we can have an idea for the solution of differential equation. Therefore, it is important to be able to approach the problem in other ways. As we have already seen, one of these ways is to draw a direction field for the differential equation, which does not involve solving the equation, and then to visualize the behavior of solutions from the direction field. This has the advantage of being a relatively simple process even for complicated differential equations. Direction field is a way to see the behavior mainly of solutions for the differential equation. However, it does not lend itself to quantitative computations or comparisons, and this is often a critical shortcoming. But when we consider a direction field, we cannot see directly an approximate value for the solution function. Therefore, we consider another alternative. It is to compute approximate values of the solution y of y is equal to phi of t of the initial value problem at a selected set of t values. Ideally, the approximate solution values will be accompanied by error bounds that assure the level of accuracy of the approximations. Today, there are numerous methods that produce numerical approximations to solutions of differential equations. Here we introduce the oldest and simplest such method, originated by Euler about 1768 year. It is called the tangent line method or the Euler method. Namely, we will obtain approximate values for the solution at some selected t values. Okay. Let us consider how we might approximate the solution of initial value problem given at the beginning near the initial point. So we know that the solution passes through the initial point t0 y0, namely we have a point for the solution function, and from the differential equation we also know that its slope at this point, which is equal to f of t0 y0 because it is equal to y prime. Therefore, we have also the slope at this point, and we know the point. Therefore, we can write an equation for the line tangent to the solution curve at t0, y0. Namely, by using the slope and the point, we can construct the equation of the tangent line at this point for the solution curve. Okay. So if you remember, we have a formula. If you know a point and slope, y is equal to y0 is equal to the slope times x minus x0, but here the independent variable is t, therefore we write t minus t0. So it is written as y is equal to y0, writing this one to the right side, plus the slope is equal to f of t0 y0 times t minus t0. This is the equation of the tangent line, you see, which is blue line in the graph, on the graph, and at the point t0 y0, which is tangent to the solution curve. Okay, using this tangent line, we can find an approximate value for the solution curve. Okay, the tangent line is a good approximation to the actual solution curve on an interval short enough so that the slope of the solution does not change appreciably from its value at the initial point. Therefore, if t1 is close enough to t0, namely we want to find the value of the solution function at the point t1. Okay, what is the value of the solution at this point? So for this we will benefit from the tangent line at the point t0 y0. So we write phi t1 is equal to y1, which is, namely, it is approximately equal to the value of the tangent line, and it is written as y1 is equal to y0 plus the slope times, instead of t we write t1, namely we want to find the value of t1 for the solution curve. The actual value will be corresponding to this one, but we can find an approximate value for this solution by finding the value of the tangent line at this point. To proceed further, we can try to repeat the process. Unfortunately, we don't know the value phi t1 of the solution at t1, but we have its approximate value, which is y1. Okay, the best we can do is to use the approximate value. Therefore, we construct the line through t1 y1, because the new point becomes from here t1 y1. y1 is the approximate value of the real value of the solution curve, and the slope can be found again by using the differential equation. Y prime is equal to f of t1 y1. Okay, so the new tangent line for the new point will be, using the general formula written here, y minus y1, because the new point has y1 for the second component, and the slope is f of t1 y1 times t minus t1. So to approximate the value of phi2 at a nearby point t2, namely t2 is close enough to t1 such that we can use this formula. Therefore, we obtain phi t2 is approximately equal to y2, which is equal to y1 plus f t1 y1 times t2 minus t1. Instead of t we write t2. Okay, continuing in this manner, we use the value of y calculated at each step to determine the slope of the approximation for the next step. So the general expression for yn plus 1, namely, first we want to find the value of the solution at the point t1, and we know the initial value, and t1 is close to the initial value, so it is approximately equal to y1, which is equal to y0 plus f of t0 y0 times t1 minus t0. Okay, t1 minus t0, where t1 is close to the value t0, which is the initial value. Similarly, if you want to find the value of the solution function at the point t2, if t2 is close to t1, so similarly we use the same procedure. Y2 is equal to y1 plus f of t1 y1 times t2 minus t1 by using the equations of the tangent lines, okay, where t2 is close to t1. And similarly, if we have a set which has n elements, so generally we can write phi n ptn is equal to yn. It is yn minus 1 plus approximately equal to f tn yn tn minus 1 yn minus 1 tn minus 1. And generally we write shortly y n plus 1 is equal to yn plus f tn yn times tn plus 1 minus tn. Okay, if we have a constant difference for the values of t, namely instead of this one we can write a constant if we have the same difference for each step. Therefore we can write this formula shortly. Yn plus 1 is equal to yn plus, shortly we write fn for this one, times h, where h is equal to tn plus 1 minus tn, and n can be 0, 1, 2, and so on. So this is called the Euler formula for finding the numerical approximations for the value of the solutions of the differential equation. Okay, this is called the Euler formula. You can see the formula here. For example, let's consider the initial value problem. dy over dt is equal to 3 plus e to the power minus t minus 1 over 2 times y, with the initial condition y of 0 is equal to 1. So use Euler's method with step size h is equal to 0.1 to find approximate values of the solution of equation written here at t is equal to 0.1, 0.2, 0.3, and 0.4. Compare them with the corresponding values of the actual solution of the initial value problem. When we consider this differential equation directly, we understand that it is actually a linear differential equation, because it can be written as dy over dt is written as y prime plus 1 over 2 times y, we write this term to the left hand side, is equal to 3 plus e to the power minus t. Here little p of t is equal to 1 over 2 and q of t, g of t is equal to the right side, 3 plus e to the power minus t. And using the method of integrating factor, easily we can find the solution of this differential equation. But let's use Euler's method to understand the concept. Using in section 2.1 we find the solution that I said to be 6 minus 2 times e to the power minus t minus 3 times e to the power minus t over 2. Using this method. To use Euler's method, we know that in this case f of ty here, let's continue, namely y prime. This is the example, and we use this formula now. Y prime is equal to 3 plus e to the power minus t, 3 plus e to the power minus t, minus 1 over 2 times y, minus 1 over 2 times y, and the initial point is y0 is equal to 1, y0 is equal to 1, which means t0 is 0, and we know h, the step size is 0.1, and the values are 0.1, 0.2, 0.3, 0.4, namely t1 0.1, t2 0.2, t3 0.3, and t4 0.4. Okay, and you see the difference of them respectively is equal to 0.1. t2 minus t1 is 0.1, and so on. Okay, first we need to find the value of the solution, namely y1. Okay, this is the approximate value of the solution curve, namely phi t1 is approximately equal to y1 is equal to, according to the formula, writing 0 for n, we get y1, y0 is 1, this is y0, plus fn, namely f0 is y prime actually, writing 0 and 1, namely f of t0 y0 is equal to, from here, 3 plus when we write 0 for t, because t0 is equal to 0, so we have 1 for the second term, minus 1 over 2 when we write 1 for y. So here we have 4 minus 1 over 2, which is equal to 7 over 2. Namely, we have 3.5. Therefore, we write 3.5 h. What is h? 0.1. After we compute this number, so we obtain, you see, 1 plus 3.5 times 0.1, which is equal to 1.35. 1.35. So f of 0.1 f of 0.1, phi of 0.1, sorry, is approximately equal to 1.35 using the Euler method. Similarly, phi t2 using the same formula, phi t2 is approximately equal to y2, which is equal to, namely we will write 1 for obtaining y2 for n. So we have y1. What is y1? This is equal to 1.35 plus the slope, which is f1 times h 0.1. What is f1? f1 is equal to f of t1 y1, namely we will write 1.35 for t1 and y1 t1 is equal to 0.2, sorry, namely we will write f of 0.2 and y1 is equal to 1.35. Writing these numbers in the differential equation for the right side, so we obtain, actually this is equal to 3.22 approximately. So we have 1.35 plus 3.32 times 0.1, so it is equal to 1.67, approximately 1.67, and so on. For f of 3 you will follow the same way. For f of t4 you will follow the same way, and you can find the approximate values of the solution curve by using the Euler method. Repeating the computation 2 more items, we obtain f of 2 is this number approximately, and we obtain y3 and y4. This is equal to actually phi of t3 approximately, and this is also approximately equal to phi t4, and when we compare these values with the real values of the solution curve, for example 0.4 exactly is corresponding to this number, and with Euler method we obtain 1.35. We found here, if you see 1.35, and you see they are very close to each other. Therefore the Euler method is useful, you see. For t2 0.2 the exact value is 1.64, and with Euler method we obtain 1.67. The error is 0.02, you see, and so on. Okay, using the Euler method, as you can see, we can find the approximate values of the solution curve of the differential equation without finding the solution. This is very useful for the differential equation, such that we cannot find the solution easily. Okay, therefore it is a very important concept. Thank you very much.